Hi, good morning, everyone, and thanks for joining the webinar. We are still seeing the attendee numbers is still increasing, so let's give a moment for people to join. We'll start the session momentarily. Let's give another minute or so. We're going to get the session started soon. Okay, I think now is 2 minutes past 11. Let's get our webinar started. Good morning again, everyone, and welcome to the AHRI webinar series on low GWP refrigerant applications. I'm Xudong Wang, AHRI Vice President of Research. I'm very excited to have you here to have a conversation today about the relevant safety standards and our latest research related to refrigerant sensor characteristics. So before we kick off our session, I just want to have a couple of housekeeping announcements. So first of all, this webinar is being recorded. We will make the recorded session available online. And second, everybody is muted. Please use the Q&A button at the bottom of the screen for comments and questions at any time. We will leave about 10 to 15 minutes or so at the end to respond to them. If we don't have enough time to address them all, and we will get back to you by email. So, okay, with this, let's get the session started. Please go to the next slide. As our industry is really transitioning to the low GWP refrigerants, and the updated safety standards will require refrigerant sensors and ignition risk mitigation features on many air conditioning and refrigeration products. So our industry really needs to understand the requirements on refrigerant sensors and the sensor's capability of meeting these requirements. So joining us today are 4 experts who have been closely working with us on standards and the sensors related issues. So we have Jim Rashal. Jim is the Chief Engineer for Trane Technologies with over 46 years of residential HVAC experience. He is the chair of the AHRI Standard 15.2 Subcommittee, a member of the UL 60335-2-40 Working Group. He is also a member of the AHRTI Flammable Refrigerants Subcommittee and has been involved in many of AHRI research projects. The second speaker is Mark Skickersplitz. Mark is with UL as a principal engineer. He has been involved with both domestic and international HVAC certification for over 15 years. He has participated on several previous and ongoing low GWP refrigerants research projects. Mark is also a member of the IEC Technical Committee on the functional safety aspects of the electronic circuits. The third speaker is Philip Johnson. Phil is a Senior Director of the Applied Development Center for Daikin Applied. He is a former chair and a current member of the AHRI Standard 15 Committee. He was a member of the UL 60335-2-40 working groups and has been involved in many AHRI flammable refrigerants research projects as a project monitoring subcommittee member. Our fourth speaker is Stefan Eldel. He is the chief engineer at Creative Thermal Solutions. He also has an appointment as a research assistant professor at the University of Illinois at Urbana-Champaign, where he serves as associate director of the Air Conditioning and the Refrigeration Center. Stefan is the PI for AHRTI project 9014 on the refrigerant detector characteristics for use in HVACR equipment. So Jim, Mark, and Phil, and Stefan, welcome, and thank you so much for joining us today. So earlier this year, AHRTI completed its project on refrigerant sensor assessment phase 1 effort. You know, we have evaluated several safety standards and their requirements on refrigerant sensors and found that these requirements are slightly different among these standards. So Jim, I bet you, your 15.2 committee has the same observation. So would you please give us a brief overview about the requirements of refrigerant sensors in the relevant safety standards? So Jim, please.
Thank you, Sanong.
Next slide, please.
Move slides. Let's go to the next slide. There we go. Oh, before we jump into the specifics on detection and sensors, I think it'd be good to go over why detection is one of the key tools in the safety standards toolbox. As we learned in the first webinar in this series, if enough A2L refrigerant leaks into a space, an ignition source such as a candle can initiate combustion of the refrigerant in a very short time. And we also know that ignition can be prevented by limiting the amount of refrigerant that can leak into the space and by not allowing stagnation of the refrigerant that does enter the space. This keeps the refrigerant diluted and eliminates any pockets of refrigerant above the lower flammability limit. So because of this, the safety standards included detection and mitigation as a key requirement for equipment that uses A2L refrigerants. Now the next slide will show the basic ways that are available to mitigate the risk when there is a leak. So the key to preventing a leak of A2L refrigerant from becoming a fire risk is by the use of air circulation by the indoor fan, coupled with limits on the amount of refrigerant that can be released into the space. The indoor fan keeps the refrigerant from accumulating near the floor, and in cases of ducted systems, distributes the refrigerant to all the rooms, ensuring that the concentration is well below the LFL. Now this can be done by running the indoor fan continuously, but of course this is not ideal for either energy usage or comfort. Therefore, the standards allow for the addition of a refrigerant detection system to the indoor unit to monitor for leaks, and if one occurs, then activate mitigation actions. These include turning on the indoor fan and turning off the compressor. It may include closing valves and refrigerant lines to isolate the indoor section, and possibly activating ventilation to reduce the refrigerant level in the space. Again, all of this is done to limit the amount of refrigerant that can be leaked into the space while keeping what does leak well mixed in the air with no pockets that are above the LFL. Now the next slide shows the standards that cover the use of A2L refrigerants in HVAC systems. There are currently 4 standards which allow the use of A2Ls in HVAC, and all of these include detection and mitigation as one of the key safety requirements. Now, the use of detection is not an entirely new idea. It has been used for quite a while in equipment rooms where the amount of refrigerant that can leak would be a risk for humans due to oxygen depletion. But it is a new approach for direct air conditioning and heat pump systems. The first standard to do this was the IEC 60335-2-46 edition, which was published in 2018. This design safety standard is not used in the US or Canada, but is widely used outside of North America. And it is the basis for the somewhat more conservative 2019 third edition of the UL CSA 60335 design safety standard that will be used in North America. And it's currently active and will be used when A2Ls have come into play. Now the ANSI AHRI standards are used in the US to cover installation practices. Standard 15 was amended in 2019 to allow A2Ls for direct systems and all types of applications. And Standard 15.2 is a new residentially focused installation standard that is expected to be published in early 2021. The ANSI AHRI Standard 15.2 will cover most residential applications. And by the way, 15.2 is currently available for public comments, and it will be for the next 40 days, and all input to that standard and what's in there is welcome. Now, these standards do have some overlapping requirements on detection and mitigation, and I'll be covering those similarities and differences on the next slide. Okay. So I've been using some of these terms already, but I wanted to, and they show up in standards, so I want to go over these definitions before we get into the details of the standards. So a refrigerant detection system, which I'm going to call RDS later on, is a system or a portion of a combination system that utilizes one or more stationary devices to detect the presence of a specified refrigerant as a specified concentration and initiate one or more mitigation actions. Now, the key to this is the self-contained refrigeration detection and alarm device, which would be similar to a CO detector or a smoke detector, is not classified as a refrigerant detection system in the standards. And mitigation actions are a series of actions taken by equipment that are initiated by detection of a leaked refrigerant and by the refrigerant detection system. And integral means mounted or mounted directly to an equipment housing and treated as part of the equipment. So that's the basic definitions. And now we're going to take a closer look at the standards. Now this is a bit of a busy slide, but if you go over the 4 boxes, you can see that all 4 standards specify when an RDS is required, how quickly the RDS responds to a leak, what must happen when a leak is sensed, and requires an hourly self-check of the RDS to make sure it's operating properly. Now there are some differences. UL and Standard 15.2 require most systems above 4 pounds of refrigerant to have an integral RDS. IEC and Standard 15 are less restrictive on the need for an RDS and allows remote sensors in some cases. And Standard 15 currently requires a yearly check on the calibration of the sensor. Now, while there are differences, the AHRI standards do require products to be listed to a recognized standard, and for the US, this would be UL 60335. And that helps keep things more consistent. And another key is that when overlapping standards are different, the most conservative version of the requirements are used. So overall, these standards are consistent with what must happen when a leak is detected, and those actions are shown on the next slide. So here are the key mitigation actions. So once a refrigerant is detected, the system must energize the air circulation fans to deliver sufficient airflow, de-energize the compressor and all electrical devices included, excluding control power transformers, control systems, and the supply air fan, open any zoning dampers that may be in the ductwork, de-energize any electrical heat systems in the system, activate mechanical ventilation if that is being used, close the safety shutoff valves if those are used. And these mitigation actions need to continue for at least 5 minutes after the detection system no longer is sensing refrigerant. So those are the key things that happen. The next slide will talk about the subtle differences. Again, 4 boxes, and as you can see, all 4 standards specify the maximum allowable time for an RDS to respond to a level of refrigerant. Now there are differences in this. The IEC has the longest time, but that standard was published before the AHRTI testing results indicated that a after response time of 10 to 15 seconds would be better. Now, the minimum amount of airflow that is required when the indoor fan is energized is also specified. And 3 of the standards have the same equation, and IEC has a lower level for ductless equipment. And in the equation, Q min is the CFM of the airflow. MC is the amount of refrigerants that's leaked into the room, and LFL is LFL. So to put things in perspective, if you use the 60 times MC divided by LFL, a 9-pound system, a typical residential system of 9 pounds would have to have a Q min of 480 CFM. So a 9-pound system is probably about 3 tons. So that's usually 1,200 CFM airflow. So it's about just a little more than a third of the amount of airflow that's required for the air conditioning system. Now, it's important to know that while there are differences here in other areas of the UL and AHRI standards, there is a committee actively working to harmonize these standards with the goal of being able to eliminate conflicting requirements. On the next slide, we'll show the other requirements of the standards on the RDS. These additional requirements are relatively consistent across the standards. Note that these requirements should result in A2L RDS systems that are what I like to call or describe as safe out of the box. No field setup, no field calibration or recalibration, and the RDSs are pre-qualified to meet the design standard by an independent testing laboratory. So thus no mistakes during installation or servicing, which is all good in terms of making sure that things work appropriately. Now the requirements are included here are sensors are tested and clearly marked for the refrigerant that is used. Wait a minute. Yeah, that's right. Sensors are tested and clearly marked for the refrigerant that is used. And requirements are that there are requirements for robustness and durability, which our next speaker is going to cover in more detail. And there's an electronic self-check with the requirement to signal a problem. And in most cases, what that signal would be that's going to activate the mitigation systems. So that completes my portion of the webinar, and I'll turn it back to Sudhan.
Yeah, thanks, Jim, for an excellent overview of the standards and how they are different from each other in terms of sensor response time requirements. Now let's turn to Mark for an overview about the sensor listing requirements. Mark, please take it away.
Thanks, Shudong. I appreciate the opportunity to speak at this webinar. Today, we're going to be talking about the details contained in Annex LL of UL 60335-2-40. This annex covers requirements specific to refrigerant detection systems for A2L refrigerants only. This is a normative section, which means that the requirements must be applied to the product if applicable. It's worth noting that these requirements apply to the refrigerant detection system itself. There's other portions of the standard that still would apply. For example, creepage and clearance requirements and plastics requirements would still apply to sensors covered under Annex LL. Before we get into some of the details of the annex, I'd like to review some terminology that we have in the standard. Traditionally, in an air conditioning or heating system, we'll have a system control board which would activate to either turn on the heat or turn on cooling, and as a result, also turns on the air handler. In the drawing that I have up on the screen right now, this traditional control board for heating and cooling functions is in the lower left-hand corner. And you can see I've labeled some of the common terminals that traditional HVAC systems would have on them. Now, for the purpose of illustrating these components, I've drawn them as separate, discrete devices. However, in the standard, there is no requirement that they be physically separate. So I'm going to start at the right side. The sensing element is the device which physically or chemically reacts to the presence of the refrigerant. Oftentimes, there will be other components for signal condition or powering the devices, which are integral with this sensing element. We refer to the overall physical package containing the elements and other circuits for the refrigerant or other circuits as the refrigeration sensor. So if you can physically pick up the parts, the case, as well as any integral components are the refrigeration sensor. Now, typically with the refrigeration sensor, that's tied to a separate control board where there's components to interpret the element output and correlate to a refrigerant value. This is the overall refrigerant detection system. So everything inside the yellow box is the refrigerant detection system. It's important that this overall system is actually what is calling for the mitigation means when the certain threshold of refrigerant has been met. For most of the investigation and the requirements we'll be talking about here in the next couple of slides, we're looking at this overall refrigerant detection system, less so on the individual sensor or the element itself. We're looking at how that system performs when exposed to the refrigerant or some of the tests. Now, as I noted a minute ago, there's nothing requiring or preventing these devices from being on one board. And it does make it a little bit more tricky when everything's contained on one board. But what's important is that we distinguish what's the refrigerant detection system and kind of draw that dotted yellow line and apply the requirements in Annex L to that portion of the board that's applicable. Next slide, please. Now, with all IEC standards, there are national differences. These national differences can modify or add or remove specific requirements to the base standard. The last option is really what we have when we look at the North American deviations. If you can click the button, please. We see that the first line of the Annex LL in the UL or the North American document replaces all of the IEC Annex LL requirements with new requirements, and we'll get into some of the specifics here in the next few slides. So once again, we've completely taken the IEC Annex LL requirements and replaced them with the UL requirements. One of the main differences that we see in the North American version of the standard is the reference to IEC 60079-29-1. This standard covers gas detectors for flammable gases. The 60079 series covers a wide variety of applications and technologies and uses, and it's important that we're only looking at the gas detector portion of the series. Now, there's an amendment to the IEC 60079-29-1 published earlier this year, so it's important that when we look at the standard, we're referencing the correct document. The only change to this was really to allow an alternate test criteria, and we'll get to that in just a minute here. Most of the testing is referenced to this standard, although there are some modifications which are allowed per the 2-40 Annex LL. One of the first ones is the calibration of the sensing device. So we will use the method defined in IEC 60079-29-1, but the deviation allows a plus or minus 15% difference for the calibration of that device. There's also included in the standard short and long-term stability. The long-term stability test is a 63-day test with periodic exposure to 100% LFL or lower flammability limit. So that does vary based on the type of refrigerant that is used. When we're looking at temperature, pressure, and humidity requirements, when we're talking about this 79-29-1 tests, we are looking at how that sensor performs at a lower or higher temperature or pressure or humidity from a nominal value. One thing to note here is the IEC or the 79-29-1 requirements have a temperature range from -20 to 55. As we'll see in the next slide, when we go talk about some of the Annex LL specific testing, we are going to also be looking at the sensor function over the entire intended range. Oh, I'm sorry, I'm not finished with that slide just yet. So there's also vibration testing called out in the IEC standard. Now this vibration testing is very similar to the existing IEC 2-40 requirements. There's also electromagnetic compatibility testing. And the interesting thing about this test is that the sensor needs to continue to function throughout the entire test. So it needs to continue to perform its intended function. And we'll get into possibly some future work associated with that in the future. But one thing to note, there are two current test methods allowed in the 79-29-1 standard. One allows a slightly larger variation over the exposure time. Now, as we look at the standard, one thing to note is that the standard itself is structured slightly different than when we typically think of the 60335 or the 60730 series of standards, in the fact that the method itself is in the body of the standard, and all of the requirements and test criteria are actually called out in table A.1 of the standard. So if you go and reference the standard and you want to see where those requirements are, it's important to look not only at the method in the body of the standard, but also in table A.1. Next slide, please. So as I mentioned, there was some specific testing required for Annex LL. And one of those tests is the response of the overall refrigerant detection system. The requirements in the standard is that the system responds in less than 10 seconds when exposed to 100% LFL or lower. Now, once again, I had mentioned before that this needs to be done over the entire temperature and humidity range. But the sensor itself, or the refrigerant detection system itself, needs to respond in less than 10 seconds. And that's calling for cooling. So this is a different value, a different response time than when we talk about the response for the mitigation in Annex GG, which is 15 seconds for that blower to, for that control system to respond and get the blower up to at least the minimum volumetric flow rate as called out in Annex GG. Also in Annex LL, we have sensor poisoning tests. On the screen, we have a variety of chemicals that will expose the sensor to. Just like before, the sensor needs to continue to operate after exposure to these chemicals, and there also can't be nuisance tripping with this. It's my understanding that the working group identified these chemicals because they could be typically seen in a household or commercial industrial environment. And the concern was that we didn't want other chemicals to elicit a response from the refrigeration sensor. Next slide. There is also some general requirements that we want to cover with Annex LL. We want the sensor system itself to be able to determine both system or sensor faults that could be open circuits, bypass sensors or shorts, as well as sensors that are out of range. Now, some sensor technologies have a service life. For sensors which have reached their service limit, the system needs to be able to provide an indication that replacement is required. And it's important to note with any of these faults, including end of life, if one of the faults is observed, the requirement is that the refrigeration detection system activate or call for that mitigation. There's a requirement that the sensor be marked with the name, trademark, or model or reference number so that it can be replaced in the field. The standard allows for replacement in the field if the end product manufacturer allows it. Note that it could be a situation where the end product manufacturer requires a replacement of the entire detection system, not only just the refrigerant sensor. Now, if there's a requirement that it's just the sensor, it is important to note that the sensor replacement would need to be the same as the existing one on the device. Next slide. So there's everything we've talked about so far has been to the current edition of UL 2-40. It was published last year in November of 2019. So even though the standard was published last year, there's already work on the next edition of the standard. Some of these requirements that have been proposed will affect Annex LL. There's been suggested revisions to both the UL CSA 2-40 as well as the IEC 2-40, which could have some impact in North America in the future. Some of the current tests that we talked about, for example, the EMC compatibility, as well as some of the other tests, require that the refrigerant detection system continue to perform as normal, but it does allow slight variations. But this is different than the approach that we've taken in other parts of the standard to abnormal tests. For example, Section 19, abnormal testing. During the abnormal tests, it allows the product to go into a risk-addressed state as opposed to continuing to function as normal, as long as we are able to mitigate there is the hazard of the refrigerant concentration is not present. There's also, as we talked about, there's some general requirements for how the sensors or the refrigerant detection system should evaluate for faults, but there's not an indication of specific faults other than some of the general ones that we went over before. So I think there's a need to improve some of the text of Annex LL in order to indicate and identify exactly what the refrigerant detection system is required to do and is capable of performing. So Shudong, back to you.
Hey, Mark, thank you so much for the great summary about all the requirements. I think over the past years, our industry has been actively learning the refrigerant sensors capabilities of meeting these requirements and how reliable they would be. And since you know, air conditioners and heat pumps last a long time in the field. So to that point, I'd like to introduce the AHRTI research project, which evaluates multiple sensor technologies. And Phil, you are the one of the technical committee members guiding that project. So would you give us a brief introduction of the project background and the key things to note when it comes to understanding sensors' response time characteristics? So Phil.
Okay, thank you, Shudong. So the impetus for this research project was to better understand the characteristics of refrigerant sensors and detection systems. You know, the industry needed an in-depth assessment of the capability for commercially available devices to meet the requirements and safety standards, or the new and revised requirements that were proposed for upcoming editions of those standards, you know, at the time the project started. Next slide, please. And next again. So the project was defined in 3 phases. The first was a review of sensor specifications as published by the manufacturers and a comparison to the requirements that Jim and Mark just outlined. Greg, could you hit next, please? Particular attention was given to response time to address concerns raised in earlier research projects. So phase 1A was a paper study that was quickly followed by phase 1B to conduct response time testing for candidate sensors that had potential to meet the requirements. Next. And the second phase of the project developed a comprehensive method of tests to evaluate a sensor's capabilities to meet these various requirements, as well as to assess its reliability by exposing it to various harshness tests. Next. And the third phase then proceeded to conduct testing with several candidate sensors as a demonstration of the proposed method of test. And it's hoped that this evaluation method or a revised version of it based on lessons learned will be adopted into an appropriate standard in the future. Next. So the project was initiated in late 2018 with a request for proposals that went out with a call for bids, and Creative Thermal Solutions was selected as the contractor, and they started work in April of 2019. And phases 1 and 2 are complete as of today, but phase 3 is still ongoing. And Stefan is going to present, of course, his work in a few moments. But first, I'd like to describe some of the issues around defining the response time of a refrigerant sensor and a refrigerant detection system. So next. So the typical specification for a gas detector or refrigerant sensor is based on the time for the output to respond to some input. Or in other words, the time for the concentration measurement to respond to an idealized step change in gas concentration. Next. So this chart shows such a step change where at some moment in time, the concentration of a test gas is suddenly increased from 0 up to some value. And the vertical scale is normalized so that 100% represents whatever the test gas concentration might be. Next, so the black line here is a typical response curve for the sensor output signal, showing the dynamics of how the output catches up to the sudden change in concentration. So if we define T0 as the time of the step change, next, the time that it takes for the sensor output to increase to a level corresponding to half of the step change is called T50. Next, and the time that it takes for the sensor output to increase to a level corresponding to 90% of the step change is called T90. Next. So this approach for rating the response time of sensors and sensing elements is well defined. You can go next, but it represents laboratory controlled conditions to create the sharp increase for a sudden step change in gas concentration. Next. However, in actual real-world applications where there is a refrigerant leak or release is known to, where there is a refrigerant leak or release, where they're known to have a refrigerant gas concentration that locally at any one point in space varies over time as the refrigerant disperses and turbulence creates eddies and mixing with air. So next. So this plot shows the refrigerant concentration at one location during a controlled release event. On the horizontal scale, the release actually starts at time 0, but note that it takes about 35 seconds for refrigerant to travel from the point of release to this particular location, and that the concentration never reaches a fixed or steady state even after 5 minutes. Next. So from the very same release event at another location, the concentration rises much more quickly, but then reaches a nearly steady state concentration after about 4 minutes. Now, note that in this example, this is a refrigerant release only for the purpose of measuring concentration and determining how refrigerant disperses throughout a space, and that there were no mitigation actions in this case. Next. And next again. So the refrigeration, air conditioning, and heat pump industry needed to know how to translate the response time ratings, T50 and T90, into practical terms and assess what would happen during actual leak or release events. Next. So another issue is that the refrigerant detection system with a fixed set point will typically have different response times when exposed to different gas concentrations. So let's take a look at some examples to explain what I mean. Next. So here we have a hypothetical sensor model ABC, which has an output response when exposed to a gas concentration that is 25% of the lower flammability limit, or LFL. Next. This very same sensor has the response curve on the right when exposed to a higher concentration of 100% of LFL. Next. And in both cases, the sensor has a T90 rating of 13.8 seconds, whether it's exposed to 25% of LFL or 100% of LFL. And what's happening here, the higher concentration drives the sensor output to increase more quickly with time, and the initial slope of the response is steeper. Next. So if this sensing element was used within a refrigerant sensor or refrigerant detection system, where you had a predefined set point, for example, corresponding to say 20% of LFL, then there would be an indication of the presence of refrigerant in 9.7 seconds when suddenly exposed to 25% of LFL. Next. However, there would be an indication of refrigerant in just 1.3 seconds if it was suddenly exposed to 100% of LFL. This is why it's important to understand that a refrigerant detection system or a refrigerant sensor does not necessarily have a single response time in actual applications, because the response time in any installation or any scenario will vary inversely according to the local refrigerant concentration relative to the set point. On the other hand, the T50 and T90 response time ratings are defined in terms relative to the size of a step change, and those ratings remain constant for steps to different concentrations. So next. So now we have a sensor model XYZ for another example with a slower response time. And just so you can see the differences, Greg, if you would go back to the ABC and then go forward, you'll see the slower response time as the black curve shifts. So the XYZ sensing element has a T90 rating that is twice as long as the prior ABC sensing element. Next. So in this case, 27.6 seconds versus the 13.8. Next again. So if using the same set point of 20% of LFL, the response time to a step change is now double that of what the sensing element ABC was. But how would the response time of these two different sensing elements compare when exposed not to a step change, but to a very different time-varying concentration profile? So next. So these plots show the responses to the time-varying concentration from the earlier example, with sensor ABC on the left and sensor XYZ on the right, but exposed to the same test gas profile. On the right, the slower XYZ sensing element has an initial response that is less steep, and the initial increase reaches a lower peak value due to the slower response time. Next. But if using the same set point of 20% of LFL, the response time to provide an indication of refrigerant is increased for sensor XYZ. However, it's not double the time. And this is due to the rate of change of the test gas concentration being much less than the idealized step change. And then next, and in the case of installing either one of these sensors in a different location, such as the other example with a lower concentration level, neither sensor would indicate the presence of refrigerant because the concentration remains below the set point, and therefore the response time is infinite, in other words. So now I'd like to hand off this presentation to Stefan to tell you more about this research project in detail.
All right, hello everybody, this is Stefan Elbo, and thanks first of all for giving us the opportunity to present here on behalf of CTS. I also would like to give credit to my colleague Joe Zhang, who did really the majority of the work I'm going to present here. Next, please. So first, a quick outline of the results and the description of the project I'm going to describe here, which is AHRTI 9014, as Shudong at the beginning mentioned, and as Phil has outlined just a minute ago. 9014 was started in April 2019. CTS is the contractor. And the project is organized in several phases. You see here the outline phases 1A and 1B. Which were the initial study to get the project really going. The first phase A, 1A was a paper study where we reviewed the relevant industry standards and looked into the currently available sensors. The way we organized this is we looked into 5 different standards that were relevant here and summarized their requirements. We've already learned about these requirements early in the webinar. Then we compiled what we call a sensor information checklist that was based on these standards requirements that we then sent to sensor manufacturers for self-assessment of their products that are available. And then we were able to check basically the requirements of the standards against the responses we got from the manufacturers and saw where there's already good overlap versus where we still have some need maybe for further development and refinement. Phase 1B was, no, sorry, go back please. Yeah, thank you. Was concerned with mostly what Phil just described with the time-varying concentrations and how the sensor responses can be derived from simple step changes. So this has to do, of course, with the fact that most concentration changes in real life, in real leak scenarios, are never ideal step changes. And I'll talk about that a little bit. We will introduce here the concept of the maximum allowable set point, which goes nicely along what Phil just explained to us, and then show you how we can actually derive these actual sensor responses for the time varying concentrations. Phase 2, just very recently completed, Then switches gear and looks more into harshness and reliability testing. Again, the method was here to first review applicable standards and make a list of requirements. We see as, in phase 1A that not all of these requirements coincide. So based on that, we had to develop a method of test and suggested that to the committee, which was recently approved. Now we're in phase 3, currently the last phase of the project, where we actually perform some of these harshness tests on 5 different types of sensors to demonstrate that the method of test that we've developed is good and sound. Next, please. The sensing principles, I should mention there's a large variety of different sensing principles out there, so many different physical principles that are employed. We have here included in this study 5 different ones. The first one is called micro-machined membrane, MMM, NDIR, which is the non-dispersive infrared, thermal conductivity based, MOS, metal oxide semiconductor, and also one the speed of sound measurement principle. And you see here how phase 1B, which was practical evaluation, and also phase 3 have almost the same. Phase 3 has one additional principle, that speed of sound, which became recently available. Next, please. So going back to phase 1A, this is, we've already seen that just from a different angle here. The requirements that are published in the current versions of the standards that we reviewed. Based on that, we basically made an overview, see where things coincide versus where they differ a little bit. The standards that we reviewed are listed here on the right side. Next, please. Based on these requirements that we found in the standards, we then designed this or compiled this sensor information collection sheet, we call this, basically an Excel table that we sent to the potential sensor suppliers, sensor manufacturers, to basically ask them for capabilities of the sensors. So you see, for example, there's different refrigerants listed. Can the sensor detect blends and so forth? We don't need to read all of this in detail, but just to give you a flavor of the level of detail of the questions that were asked. We sent the list to 26 potential sensor manufacturers that we identified through various ways. We talked, of course, directly with OEMs. We went to some trade shows and identified these initial list of 26 potential manufacturers, and we got 11 completed surveys back. Next, please. After we got this self-assessment from these 11 manufacturers, we were then able to cross-check how do the sensor manufacturers assess their own technologies versus what are the requirements in the standards. You see there's a lot of green. Green means good. There's a few reds that basically show where particular sensor manufacturers would not be able to fulfill a particular standard requirement. And then the yellow ones are, a maybe, where maybe we need to look a little bit more closely. Next, please. This here is for phase 1B, so that was that first phase where we started to work with actual hardware. And again, the initial task was to create a facility that can give us reliable step change responses. That sounds on paper very easy, but once you actually set up something, it is a little bit more tricky. What we decided to go with here is what we call a so-called push-through facility. Push-through means you see on the bottom right here what we call the zero air chamber. So this is where the sensor is stored at the beginning. It has exposure to clean air. Once the actual test starts, it is switched into the actual test chamber, which is shown above it. And in that test chamber, there is a pre-mixed concentration of the test gas of interest. How do we mix this? We have on the left here in yellow that refrigerant tank that is held at constant pressure conditions. Then we have a flow controller with which we can meter the flow rate of refrigerant. We measure with an accurate refrigerant mass flow meter, and we mix together with clean air that got compressed with outside air. So we are not recompressing some of that vented refrigerant. There's some conditioning on the air side in terms of air cooling and humidifying. Again, very accurate measurement on that air mass flow meter. Some of that air here is bled also into that zero air chamber. You see that on the bottom. Then finally, we mix the two streams of the metered refrigerant mass and the air mass together. We mix them, and diffuse them into the test chamber. So once the time for the test comes, we grab the test sensor from the zero air chamber and push it through the test chamber on the top. There's a micro switch, so we know exactly when to start. How do we measure? With two different independent methods here. We have a reference sensor that is based on thermal conductivity principle, and that is more than one of the test sensors that is actually a higher quality kind of sensor with high accuracy. And of course, it's for lab measurements, not for mass production. The other independent measurement method is based on this refrigerant and airflow device, which we have validated also to give very accurate results. And so we have two independent measurements. Again, what I was trying to say earlier, it is not very easy to make these ideal step changes. We have managed to do this here. So with this kind of push-through facility, it is possible to get these step change responses. On the right side, you see some pictures of the equipment. I think by now you had time to look at the picture. Next, please. So these are some of the typical sensor outputs. So we see on the left side the typical step change response. So you have a concentration jump, and these are actual measurements here. And you see how the sensor output follows, very similar to the kind of principal schematics that Phil just showed. On the right side, you see here the sensor output tracing a variable concentration kind of injection. So you see how the test gas concentration changes over time, and the sensor output varies. So on the left side is what we have in lab experiment. On the right side is what we have in reality in real leaks. Next, please. So let me talk a little bit about the concept of this maximum allowable set point. What does it mean? It means that for the same test gas concentration, it depends on the set point or the threshold here. Depending on how you choose the set point, you will have a longer or shorter time for the sensor to trigger the alarm. So that means if you have a slow but maybe very reliable sensor, reliable meaning that you don't have any false alarms, any wrong trips, you can make use of that, even if the sensor is a little bit slow, to use a lower set point, and that way you can still comply with required response times. The issue we have identified here is that because in the different standards, we see different time requirements that are listed in the individual standards. There will be more than one maximum allowable set point. Sounds a little bit confusing, but maybe in the next slide you will see what I mean. So definitely what would be helpful is if the standards are a little bit more uniform in terms of their requirements, or the manufacturer is able to pick the most conservative set point to address the standards of interest. Next, please. So you see here what I mean by that maximum allowable set point. Let's first look at the left where we have the graph. You see first a bunch of graphs. The dark orange here means that is the average value of that bunch of curves of the lighter yellowish color here. So let's focus on the darker orange. If I have now, in this case, I have looked at AHRI 15 and I see 2-40. And we see that both require test gas concentrations of up to 25% of LFL, so that is the same. However, the time requirements are different. So one is 15 seconds, the other one is less than 30 seconds. And because of that, you see that the same sensor, so we have here test sample sensor A, would require two different set points. So in order to make the more restrictive time, the faster time, you would have to set the set point to 16.4% LFL. The slower allowed time response of less than 30 seconds would give you the possibilities to set to 21.7% LFL. Next, please. You see that if we add another standard, so you see here UL 2-40, which requires a different test gas concentration, here all shown in blue, is the 100% LFL. You see the time requirement is even more strict at 10 seconds, which means the resulting set point, maximum allowable set point, has increased here to 32.3% LFL in order to meet these requirements. So this just shows that depending on which standard you follow, there is different maximum allowable set points. Next, please. Let's talk a little bit more about the step changes and the response to these actual time varying responses. So we already learned there's time delays and time constant that can be identified based on a simple step change. Step changes, just to recall, are those kind of responses that we get with that test facility I introduced. And it would now be very nice if we could use a mathematical model to predict then later the actual sensor response to these time varying concentrations once that step change response is known. Unfortunately, this is possible, and I'll show you how we do this. Next, please. So you see here first on the left, we use these different samples that we had, so sensor A, B, C, D, and so forth. We use 2 different samples each to get some average value. And from that, we identified the time delay until the sensor output starts and the time constant of the step response. Once we know that, next please, we go into our dynamic response modeling, and you see now here in red that U of T is basically time varying response, time varying gas concentration. And based on these identified sensor characteristics in terms of time delay and time constant, we can make use of linearization and control theory. We can basically use linear transfer functions and then model what the sensor response would be if we don't have this steep step change, but this time varying profile. Next, please. And you see exactly this happened here on the right. So you see in blue is an experimental value for some time varying test gas concentration. You see how it increases here on the right. The sensor output here is in gray. So again, actual measurements. And you see how with that system characterization, we were able to very accurately model the output of that actual sensor. So in other words, it may not even be needed to measure the sensor output for these time varying concentrations once we know the step change response. So we show that these 2 can be linked. Next, please. And this shows again the entire recipe, how we do that. So starting from the step change, the modeling part, and then getting the actual response. Next, please. Let's look at phase 2. So this is concerned with harshness tests and designing a method of test for these harshness and reliability tests. Similar approach here. We first reviewed the relevant industry standards. They are listed up here. And then based on that, we compiled again a list of requirements to best capture what the different standards prescribe. And we were able to identify 5 basic categories. So the first one is fluid resistance and poisoning tests, basically addressing how the sensors behave when they're exposed to other kind of fluids, liquids, oils, and so forth. Then there's a category extreme storage condition test. So what happens, if the sensor is stored at very high, at very low temperature, and then, is it still accurate later? Then the so-called operation condition tests. So this is testing under very high temperature, different pressures to simulate different altitudes and so forth, different supply voltage and whatnot. Category D, you see here, is vibration and impact. The standards are pretty elaborate on this one. And then we have a repeatability test, which is a longer term and a short term stability test. Next, please. So based on this, we have identified the method of tests. So here for these individual categories, we have summarized what we believe are the most important stresses to investigate. So you see here a list of fluids that should be investigated. Some of the common kind of contaminants, products like coil cleaners, oil, pure refrigerant, and so forth. Storage test goes, as I said, from very low to very high temperature. Then under operating condition, there's some tests, again, with temperature and humidity, but also condensation tests. So we have liquid water on the sensor. Pressure testing to simulate the high altitude. I show the facility in a second here. Then some tests with different air velocities from different attack angles and so forth. And some of these other tests. Next, please. Then the facilities that we use, we have here a refined and improved version of what we call the push-through facility, basically that got automated. You see now on the top here, that white cylinder is the zero air chamber. And then once the time is right, it automatically transfers the sensor down into the test chamber that has the actual test gas concentration. We, in addition, made some additional facilities here for the gas injection tests. So this is a vessel that contains the test sensor and some agitation for the airflow. and then we can inject a known quantity of the contaminants that we want to investigate. The pressure test facility is kind of interesting. It's an additional feature as shown to the left here with an airbag. So it's a deflatable and inflatable bag that we can use to vary the pressure inside the test cell. So with that, we can then inject also our test gases at different environmental pressures. The larger facility on the right here shows what we use for the operational test conditions. It contains basically of an environmental chamber with all the temperature and humidity conditioning equipment that is needed, and then combined with that push-through facility. That whole facility is then basically conditioned to the temperatures we are interested in. Next, please. Here you see for phase 3, we have received 5 different sensing principles, so sensor samples with these 5 different principles that are listed here. So we have identified these different harshness test scenarios, and this is what's now being investigated. On the left here, the images of the test samples. On the right here, another image of the test facility. Next, please. Next, please. I can show you here some preliminary data that we got from some of these harshness and reliability tests here from the category A, fluid resistance and poisoning tests. These are tests obtained with CO2. What we're interested in here is, does anything change with the sensor before and after exposure? So first we check if the response characteristic is still the same. Did the sensor get slower, faster, whatnot? And you see that red and blue here coincide very nicely. So it doesn't seem to have any effect that exposure to these 5,000 ppm of CO2 if we check before and after exposure. In terms of accuracy, we try to hit different test points or set points in concentration here you see. So you see that even before and after exposure to the 5,000 ppm, there's no difference, which means the sensor seems to maintain the same accuracy. There's some other fluids that we've already tested, carbon monoxide, ethanol, and some siloxane also. Next, please. The picture is a little bit different for the test results during exposure. You see here, this is going on while we inject those 5,000 ppm of CO2. And you see that we have sensors here that react to that. So 2 of the tested sensors clearly show that there's a few percent of change in LFL, in concentration sensor output. And what that means is if you're operating relatively close to a set point, of course, this kind of behavior could trigger at some point a false alarm. So this is something to look out for. Next, please. These are the tests that we are still completing now. Some select points, again, to validate or to demonstrate that the method of test we have developed is good. So those are the tests. I don't think we need to read in all detail. I already introduced the matrix. Next, please. And this brings us to the conclusions. So from the first phase, we have seen that there's already a good number of commercially available sensors that can meet the requirements in the relevant industry standards. So that is good news. We have also identified, of course, that there's some consistency issues between the major standards. So a more uniform approach would be good, because otherwise we end up with what I've demonstrated here. That for 3 different standard requirements, you know, we have 3 different maximum allowable set points and those kind of inhomogeneous kind of results. However, after adjusting the set points, we were able to demonstrate that the sensors we evaluated had great potential. They met the response time and accuracy requirements, so there was no concern from that, but it required a little bit of tweaking and you know, really adjusting these set points. That's a very important point. What we've also seen is among the sensing principles tested, and this is not to endorse, you know, any of the technologies, but this is just an observation that the thermoconductivity-based sensing principles so far has shown good accuracy, highest accuracy, and also fastest responses. Doesn't mean that it couldn't be achieved with any of the other ones. The sensor response time to time varying concentration we have shown can be accurately predicted. So this is good because we don't need to do all of these experiments. We only need to do the relatively simple step change. Once that is identified and characterized, then we can predict how the sensor would behave in real life. And then finally, besides the response time and the accuracy, we are also looking into robustness, reliability, and harshness. And this is what we're currently investigating in phases 2 and 3. Next, please. What's already published, what's already available, and I show the link here, is the phase 1 report. So those are phases 1A, 1B. I expect that the phase 2 report, which was just recently last week approved by the committee, should be available very soon. And with that, please, my last slide. Next. We expect to wrap up phase 3 by early next year. So there's still a few more tests to do, but we're on track with the schedule. And then, of course, those latest results in phase 3 will also be published, same as phase 2. And with that, that's all I have prepared, and I give back to Shudong.
Hey, Stefan, thank you for the great presentation. Again, thanks all speakers for the talks, and there is definitely a lot of information. So we got several questions and comments coming in while we're talking, and some of them were already answered by speakers, but there are some unanswered questions, and let's take a look at them. I think looking through the list, and there is several questions about the sensors, and I think this, even though this one was answered, I think it's still worthwhile talking about. Is how do we know if the sensor fails or is not working properly because of either aging or it's at the end of life and so on. So I guess this is maybe Jim or Mark and Phil, and you guys are working with AHRI standard 15 or 15.2 or UL standard. Can you shed some light on that?
Shudong, as Jim, the hourly self-check is an electronic check on the sensor to assure that that sensor is still working appropriately. And exactly how the electronics are going to do that will probably depend on the sensor and on the approach that the designer wants to take. But that was the reason for the hourly self-check. If it's not sending a signal that's in range, it's gonna go into default mode and turn on the mitigation actions. And maybe Mark could have more information on that.
Yeah, exactly. There's a variety of different control system mechanisms where you can validate the performance of the sensor, certainly for like an open or short condition, to be able to monitor that, as well as through either hardware or software, determine whether a specific sensor is outside of an intended range, and from there you can assume that there's some sort of fault and activate that mitigation means. So as Jim mentioned, yeah, the intent was that in the event that there was some sort of open or short or failure, that the refrigerant detection system would call for that mitigation, and we would go to that risk address state.
So Mark, as a Jim, could you go over the safety circuit requirements that would occur on that RDS as well?
So that's a very good question, Jim, and I think that's something that needs to be clarified a little bit more moving forward. When we take a look at the refrigerant detection systems, or I shouldn't say refrigerant detection systems, but protective electronic circuits in the bounds of the 60335 series of standards, we have specific criteria that we're looking at for components opening and shorting, as well as looking at software characteristics that allow us to mitigate against anticipated faults. So as it currently sits, we don't see that same sort of approach with a vast majority of the refrigerant sensor manufacturers as it sits today. So I think there's some opportunity to clarify both what's required for any software or hardware that may exist as part of the refrigerant sensor. Keep in mind that refrigerant sensor could be a separate device from the control board that's interpreting that signal and actually calling for mitigation. So I think there's some opportunity to improve the standards both at the North American level, as well as improving the requirements and what's specifically required at the IEC level as well.
Thank you, Jim and Mark. I think Another question is related to calibration accuracy. I believe that one might be related to Mark, your presentation. That's the question is minus plus 15% calibration accuracy. Is this dependent on the threshold level one chooses, or minus plus 15 of 25% of LFL?
Yeah, so the question on where the threshold needs to be is something that is going to be specifically defined by individual manufacturers. Some may take a more conservative approach, or as Phil and Stefan mentioned, they could set a lower threshold due to a longer response time for a certain refrigerant characteristic. So by doing that, we are looking at the calibration of that sensor, not only at that specific defined threshold, but the 79-29-1 is actually looking at the response of that sensor over a fraction of the LFL values as well. So we're not only looking at the threshold, but also that calibration curve for lower percent values as well.
Thanks, Mark. I guess the next couple questions is really to maybe for Stefan, and one of them is, when you tested those sensors, did you test those refrigerants and or will you test the refrigerant and other competing gases and vapors at the same time, or you test them individually?
Yeah, for those tests, there's first to see while it is exposed only to that foreign substance, if that would change the accuracy once the sensor is in exposure to the design fluid again. So in other words, we do that first with R32 before we expose to anything. Check what is the output, and then expose it to, for example, CO2 or carbon monoxide only. See what is the output. If it changes, that was that after the exposure, those slides that I showed, during the exposure, excuse me. And then afterwards, we take it back into the R32 operation and check if anything has changed. So it would be a separate test here.
Okay, thanks. And what temperature range will the sensor be tested to?
That was shown in some of the earlier slides, and of course, all of that will be in much more detail in the reports. The storage right now is, let me just look up the numbers just to make sure we're not saying anything wrong here. Right now we are at minus 25 up to plus 60 degrees C. And for the operation test, we have currently 55 degrees C at a specified humidity range, and down to minus 20 degrees C. So those are the tests we are performing. But again, the method of test that we have developed due to the time and budget constraints, there will be additional temperatures that we, at this point don't show, because we have picked the more extreme conditions, basically.
Thanks. Okay, and I think there is another question about the talking about standards. How can these standards be met with split systems, with mixed matched systems? Compressor, condensing unit, indoor coils, and furnaces, and all separate things.
So on that one, this is Jim again. That's going to be interesting. The simple systems with 24-volt controls will probably be doable, because I think the RDS will end up being between the thermostat and the furnace, and so it'll go through there and it'll send signals to the control board to go and do whatever. And when you get communicating controls and sophisticated systems, that's going to be more difficult. And there's going to be some work done on how to make sure that it happens and happens safely.
Thanks, Jim. Now we have time for one last question. I think that pertains to Phil. So, based on your presentation, is it a general observation about, you know, in more realistic scenario, it's more like time varying test would generally apply, but for the sensor readings would be a step change test.
Shidong, I'm not entirely sure I understand the question.
Sorry. Yeah, the question, let me rephrase is, in real application, what scenario does a step change test represent? Or what about time varying test? Yeah.
Yeah, so I mean, a step change would represent a very rapid release of refrigerant, you know, particularly if the refrigerant sensor or sensing element was directly at the source of the release. So there's no delay, you know, no time delay due to, say, you know, the time it takes refrigerant to disperse or flow or be transported to where the sensor is located. And then also a very, you know, large leak, meaning a very rapid rise of concentration where it would approximate a step change. All
right, thanks. I guess that will conclude our session. And so if you have additional thoughts, then please contact us. And Gregory, could you move to the next slide? We have the contact information there. And so please contact Helen or me for those projects. And also, I hope you enjoyed the contents of this webinar, and will join us on October 14 for the webinar 4 about refrigerant modeling effort. We thank you all for coming, and thank our speakers. And now the session is concluded, and enjoy the rest of your day. Bye now. Thanks.